In this lecture, we will look at greedy algorithms. It is an algorithm design paradigm where we choose the locally optimal solution at each step. Typically it is an iterative method or recursive method, and at each step we look at what seems best currently, and then we pick that and proceed. So you have already seen a couple of greedy algorithms. For example, you may all aware of the Dijkstra's algorithm for finding shortest path. That is a classical example of greedy algorithms. So in this lecture and in the next lecture, we'll see some more examples of greedy algorithms. And as I said, it at each step the greedy algorithm picks the best solution or best step towards the solution, which uh, may not always lead to the optimal solution, the global optimal solution. So whenever you have a greedy algorithm, the proof of correctness becomes extremely important, and that is typically much more non-trivial and interesting than the greedy algorithm itself. So our first example problem is storing files on a tape. So tape is a sequential device, and you need to store the files. We have n files, and we need to store the files on a tape so that each files can be accessed quickly. So we have n files, and their length is stored in the array L1 to n, and so suppose this tape you can think of is as a very long sequential device. And suppose here the first file is of suppose this length, suppose the second file is shorter, the third file is larger, and so on and so forth. So we need to decide in which order the files will be stored, and what is the cost of accessing the kth file. So suppose pi be the permutation which is basically the order permutation according to which files are stored. Okay, and what is the cost of accessing the kth file? So suppose this is pi 1, this is pi 2, and so on. So just for concreteness, let's first ensure that all of us has understood. Suppose this length array is the first file length is 7, second file length is 2, and third file length is say 5. And there are 3 factorial ways of storing these files on the sequential device, which is a tape. So let's fix a permutation. Say suppose I store the third file first, then the second file, and then the first file. Then how will the tape look like? The third file is stored first, which takes 5 units of length. Then second file is stored, so it is stored from 5th location to 7th location, and then the first file is stored, which takes 7 uh, 7 size space, 7 units of space, so this is 14. Now to access the first file, to access the, so this is called, say, file 1, file 2, file 3. So what is the cost of accessing the first file? The first file is stored here. So because this is a sequential device, to access the first file, the head of the magnetic tape needs to scan through the, first needs to go from 0th location to 7th location and then read the first file. So to read the file F1, it needs 14 amount of time. Similarly, to read the file F2, which is this, it needs 7 units of time, and so on. Okay, so let's define it formally. Cost of pi k, which is the kth file according to the permutation. To access the kth file, the head of the magnetic tape needs to scan past all file from pi 1 to pi k minus 1 and then read pi k. Okay, and now suppose that all files are equally likely to get accessed. So suppose all files are equally likely to get accessed. So expected cost is file, there are n files and each file gets on an average 1 out of n times gets accessed. So expected cost is the average cost, you can think, cost of, say, pi k by n, k equal to 1 to n. So this is the average cost. So let's just write what is cost of pi k from here. This is summation k equal to 1 to n, summation I equal to 1 to k L of pi I. Okay, and what is the goal? Goal is compute pi which minimizes expected cost. So even in our toy example with 3 files, you will see that various permutation of the files will give rise to various cost. So for example, here what is the expected cost in this one, or average cost is for the file F1 I need 14 units of time. For file F2 the cost is 7 and for file F3 the cost is 5. The average cost is this by 3. So 21, 26 by 3. we'll see that if we change the permutation, for example, if we swap the file 2 and file 3, then the cost will change. So for various permutations, you will get various costs, and our goal is to compute the permutation which minimizes this average cost. Okay. Now, what is the intuitive? What does our intuition say? How the files will be? How the files will be stored? If you think a little bit, it does not make sense to store a big file at the beginning, because that file you have to access it many times to access any file which is stored after that. So intuition says arrange files in non-decreasing order of length. Okay, so the algorithm is sort of very simple, that you simply sort the files according to the length, and that's it. Or that seems to be the best permutation. Now, as I said, so typically the greedy algorithms are very easy to explain and implement, but it is trickier to prove it. That indeed the greedy choice, the locally optimal choice that you are making, is indeed the correct one. For this case, although this is easy to prove, what we will show is that any other choice is not optimal. So here is a theorem. Expected cost is minimized when your permutation, you are storing file in non-decreasing order of length. When L of length of the ith file is not more than the length of I plus 1th file. This is for all I in 1 to n minus 1. Okay, and typically this proofs for proving optimality of greedy algorithm is often is done by contradiction. So here also we will do it by contradiction. So suppose pi is so expected cost of say pi, let's write it, because the cost depends on permutation pi. So suppose expected cost of pi is minimized, but this condition does not hold for all I. That means suppose, if possible, there exists I in 1 to n minus 1 such that L of pi I is strictly greater than L of pi I plus 1. That's what it means, that this condition does not get satisfied for some I. Okay, that means what? That means here is the permutation pi, and here is this file pi I, here is this file pi I plus 1, this length is L of pi I, this length is L of pi I plus 1. Okay, and we need to show, we need to find some contradiction. Now, contradiction to what? What we have assumed. So, the only statement that we can contradict here is that this pi is an optimal solution. Pi is a permutation which minimizes expectation of cost pi. That was our assumption, and we will contradict that statement. How will we contradict that statement? The most natural way is that you come up with another permutation, say pi prime. So this is pi, and show that expected cost of pi prime is strictly less than expected cost of pi. And what is pi prime? There is no price for guessing. There is an easy guess. You exchange pi I and pi I prime. So in the ith location, pi, you are storing pi prime I, which is nothing but pi I plus 1, and pi prime I plus 1 is nothing but pi I. So what is this length? This length is L of pi prime I, which is nothing but L of pi I plus 1 and this length is L of pi prime I plus 1, which is same as length of pi I. Okay. Now, can you tell me what is expected cost of pi minus expected cost of pi I prime? Pi prime. So, I will let you verify formally that this is, just expand these two individual terms, expected cost, and you will see and use this that pi prime I is pi I plus 1 and pi prime I plus 1 equal to pi I. This will be 1 over n L of pi I minus L of pi I plus 1. So you can verify this, but intuitively all the files before this I and I plus 1th file, before and after this I and I plus 1th file, they contribute same to the expected cost, and when you take the difference, those terms cancel and the remaining term becomes this. Now, because length of pi I is strictly more than length of pi I plus 1, we have this is strictly more than 0. And hence, what we get is expected cost of pi is strictly more than expected cost of pi prime, which is a contradiction. That shows that pi, that contradicts to our assumption that pi was a permutation which gives the least cost, least expected cost. Our next example slightly generalizes this problem. So, suppose we are also given access frequency of each file. Access frequency of each file. This is, suppose this is f12n. So to compute the expected cost of a permutation, we assume that all files are equally likely to exist, or they are accessed same number of time. Now suppose we are also given that ith file is accessed exactly fi times. So then what is the cost of pi now? So let's define cost of pi, because there is no expectation here. Each file, how many times it is accessed exactly is given. So k equal to 1 to n. Now what is the cost of accessing the kth file? This is summation L pi I equal to 1 to k, and this particular file pi k is accessed if pi k times. Okay, so this is our expected cost. So maybe you can also write it equivalently as k equal to 1 to n, I equal to 1 to k, L pi I if pi k. Now let's think of some simpler problem where the length of each file is same and only access frequency differs. Then how should you, or how should we arrange the files so that the cost of pi of that arrangement is minimized? Again, the same heuristic, same intuition tells us that you arrange the files in such a way that high frequency files which are accessed frequently is stored at the beginning, and low frequency files are stored at the end. And using this similar exchange argument, so this particular argument is called exchange argument. This is informally called exchange argument. This type of exchange argument is quite common while proving optimality of a greedy choice. Okay, so using similar kind of exchange argument, you can show that if the length of all files are equal, then it is best to arrange the files in non-increasing order of their frequency, which and that particular order minimizes the total cost. Now what if both of them vary? That means the file lengths can also be different, and the access frequencies can also be different. And then it turns out that the greedy choice is sort files by L by F. Okay, so arrange the files in non increasing order of L by F. Okay, so again, because this is a heuristic, we need to prove that it is optimal, and that's when it becomes, the algorithm becomes correct, and we'll be sure that this local greedy choice indeed leads us to an optimal solution. So here is again a theorem that cost of pi is minimized when L of pi I by f of pi I is less than equal to L of pi I plus 1 by f of pi I plus 1. This holds for all I in 1 to n minus 1. Okay, and again the proof is exactly very similar to our previous proof. Let's repeat it for the last time maybe. Again it is proof by contradiction. So suppose there exists I in 1 to n minus 1 such that this inequality does not hold, such that L of pi I by f of pi I is strictly more than L of pi I plus 1 by f of pi I plus 1. Again, what should we do? How will we find a contradiction? We will find another permutation pi prime which gives less cost than pi, which will contradict our assumption that pi is a permutation which minimizes the cost. Okay, so define define pi prime same as pi except pi prime I equal to pi I plus 1 and pi prime I plus 1 equal to pi I. You swap pi I and pi I plus 1 and then you get pi prime. Okay, and then again let's see cost of pi minus cost of pi prime. Like before, all the other terms gets cancelled, and what you can show is that this is equal to L of pi I times f of pi I plus 1 minus L of pi I plus 1 times f of pi I. Okay. Now so what you can do from here is that you can take f of pi I times f of pi I plus 1 common, and you can write it as L of pi I by f of pi I minus L of pi I plus 1 by f of pi I plus 1. Okay. Now because the first term L of pi I by f of pi I is more than the second term, then this is strictly greater than 0, which implies that cost of pi is greater than cost of pi prime, which is a contradiction to our assumption that pi is a permutation which minimizes this cost. Okay, and again you can see that we have the same kind of exchange argument while proving that our greedy choice leads to an optimal solution. What is the running time of the algorithm? You can check that the running time is dominated by it is only sorting. So the running time is order n log n plus the so if you only need to decide the order, the permutation pi, then it is order n log n if we use any efficient sorting algorithm. Okay.